Hi everybody. Here I have taken a 10-story office building. It has 6 bays of 7.5 meters in the east-west direction and 3 bays of 6.5 meter in the north-south direction. All columns are 400 millimeter by 400 millimeters, and the edge of the building extends 200 millimeter beyond the center of exterior column. You can see it here. I put the dimension from the center of this column to center of this column, but there is remaining 200 millimeter here outside, here 200 millimeter outside. So our target is to design this shear wall to resist north-south direction wind loading acting on the long side of the building. This is the long side, and long side of the building that wind is acting. This wind load is acting. So basically this is my second part of this shear wall design video. First part, already I explained how I calculated the wind loads. Here I am going to calculate dead load and live loads. So let's move. As I said, wind load already I showed it other video, first part. Only I am giving some highlights of that. So these wind loads, in my first part I already showed how I got these values. As well, this is the shear diagram, story shears, and this is the moment diagram for each floor. How I got this, you will find it in first part of my video on these topics, shear wall design. As I said, here I will find dead loads and live loads on shear walls. So to get that, I have to know first what are the tributary area from the floor is on the wall. That is why I wrote a tributary area to the wall. So if I know what is the tributary area, so it is easy for me to find the total load, dead load, live load acting on this shear wall. So how I get tributary area? Already I showed in previous slide. This bay, each bay is 6.5 here, 7.5 here, 6.5. So 7.5 from center to center, it will be 7.5. And here also this is center of this base, so this part and this part it will give 6.5 and this is 6.5, so total is 13. and this length is 7.5 from center to center. So if we multiply, we get 97.5 meters square. This is the tributary area to the wall. So in the next all the slides, to calculate the loads, we have to use this area, I mean tributary area. So let's move. We can see that here in Excel, I shall estimate the size of the shear wall. If the wall stiffness is constant over the full wall height and the wall is fixed at the base, also the maximum slope of this wall, it happens in the top story. So our target is to find the slope of the wall at the top of the structure, and it is given by this. Slope at top equal to rotation of base of wall plus area of M by E diagram from base to top. As well, if the base is fixed against rotation, then slope at top, it is given by this formula. Here Ws, wind load per meter of height, Hn, height of the wall, Ec, modulus of elasticity of concrete, Ig, the gross moment of inertia of the wall or walls. Now, as per NBCC, National Building Code of Canada, limits the maximum story drift under unfactored loads to 1 by 500 of the story height. So in this situation, setting the slope equal to 1 by 500, so the minimum total Ig for the walls parallel to the wind load can be computed as this one. So once we find this, that is minimum total Ig. This is very important point to understand. The value we got here, it is minimum total Ig. So all these factors like Ws, Hn, Ec are here. This is the formula to calculate Ec. A prime C is given, W, it is 58 kilonewton per meter. But one important things I want to tell here, as I say, Ws, wind load per meter height of the structure at the top of the building. But how to get that? This is actually windward pressure, leeward pressure. In my first video, I showed it is in the table. There was a two columns, one was for windward, another is leeward pressure. So from that table I have taken this. So adding these two multiplied by the width of the building, 45.4. Width of the building means, if we look at here, from here to here, this width, it is 45.4. And height 36. So putting all those, we get this, and if you click it, you see the equations same as this one I used. Taking the cell address, I got 9.01. Now we can try a size. How to get the size? First we have to assume, say it is 0.25, because we know the Ig. So we can take a planar wall. So wall width be equal to 250 millimeter and LW 7.56 meter. It gives this amount of Ig. And this is the minimum Ig we can use, minimum. So the one bay walls in the north-south direction would have a length 6.9. How it comes? 6.5 plus 0.4 for the column. Because this one 6.1 bay width, this is 6.5. So 6.5 from here it will be extended 20, here to be extended 20. I mean 0.2, 0.2. So it is 0.4. That's why length of the shear wall it is 6.9. So we assume two walls like this, 6.9 length and width is 0.25. This one is for this direction, so I am not worried about it now. My target is to calculate this one as well. This one will come automatically because both are same. It is symmetrical. Now we need to compute the dead and live loads on this wall 0.25 by 6.9. So here I calculated the shear wall area 1.725 because tributary area 7.5 by 13. How it comes? Because this bay width is 7.5. From center to center it will be 7.5. 13, 1 bay 6.5. This is half of the bay. This is half of the bay. So this part it will give another 6.5. So total is 13. So multiplying these two we got 97.5 here. Subtracting the shear wall area, we got the area for the live load. Now, here under the column there is a drop panel, so that load is here. Partition and superimposed dead load is given like this. Dead load per square meter of slab 4.8. So totally we get 6.45 kPa. Once we get, this is actually per square meter. So total uniform load per story, surely we have to find this by multiplying by tributary area. Already we know that 97.5, so we got 629. Now question is, in this tributary area there is a load from this wall also. So what is that load? 0.25, 0.69, 3.5 is the height of the wall, 24 density of concrete, so we get 145. Now adding these two, we get this total load on wall from one typical story 744. Only small difference will be because first story our height is 4 meters, so wall load will be slight more. How much? 166. So instead 144 we have 45, we have to calculate this load, or we have to take this load for first story 166. Now we got the loads. Now we need to calculate how much is the dead load, snow load, unreduced live load, tributary area, live load reductions factor, and reduced live load. Then reduced live load plus snow load, we will get the total live load because snow load also a live load. Now how to find the snow load? We have to use this formula equations. Formula how? Here SS, it means ground snow load 1.6. As we know, roof snow load always less than ground snow load. We are trying to find the snow load on the roof. So surely we have to multiply this SS by some factor, that is 0.8, because this is roof snow load factor. So 1.6 multiplied by 0.8. As well, we have to add another load that is called associated rain load. It is 0.1 kPa. So totally we got 1.38. All other factors, it is all assumed as 1, I mean normal. This one. Snow load, we got this. So total snow load surely, if we take this tributary area, multiply this, so we get the total snow load. So we got here 135 total snow load. And here, if you look at dead load, 774, we got it here, 774. This dead load here, snow load here. Now, we can move fast. This snow load to be kept for all the rows, I mean all the floors, and this to be also calculated. It will be according to, if you look at 774, then if you go for this, then what you found? Of course, this is I-94 and O-84. O-84 means what? This one. O-84, this one. So this way we can calculate. Clicking here, if we pull it down, all the values will come. 135, we are putting all the floors same loads for the snow loads. Unreduced live loads 460, we calculated here this one. How? Live load we know 4.8, so same way multiplied by live load tributary area. We have to deduct the shear wall area. We got 95.8, so 95.8 multiplied by live load, we get this 460. Same way we can go for all. We find it because if we click here, we can see that L95, F95. So L95, it is the previous one. F95, it will be this one. And clicking here, pull it down, you get all the values. Tributary area, we can find it same way. This live load also, if you look at, I click here, you can see the cell address. Then go for reduced live load, I mean live load reduction factor. How it is? We have to use this formula to find this. So once we get this using this, and also this way, because once we take this, you see the value of B, it is the value of this one, M95. When I click here, we have to put the value B, it is this one. Again, if I click here, this B will be this one, M99. So once we get this, then reduce live load. How? This value multiplied by this, we get this. This value multiplied by this, we get this. So once we get this, now reduced live load we have and snow load we have. So adding this, we get here. Again adding these two, I mean this one and this one, we get this value. So total live load, we got it. That was our target, to calculate the total live load. Dead load already we know. In the first floor, it is 7758. And total live load at the first floor, it is 1817. That's what I have written here. 7758, 1817. So here there are important things we need to understand. Compute the factored load acting on the wall. We know dead load, we know live loads. Now compute the factored loads acting on the wall. So there are 4 combinations: dead load, live load, dead load, wind load, and here also dead load, live load, wind loads combination. You can read it combination 4, this one. But we will use these two combinations. The reason is for largest axial load will come from combination 1, largest axial load. So we are using this combination 1.25, this one 1.5, this one, we get this 12424 kilonewton. We got it, axial load only. When we go for combination 4, it is 0.85 dead load, 1.5 W. This is actually, it is wind loads. So these wind loads, all the, how I got all these values, in my first part of the video I explained everything, how to calculate the wind load, how to get this shear force, moment force diagram, shear diagram. So here if we look at, you see here at the first story, first floor, 35376, that's what I have taken here, wind loads. And this is shear 1787, dead loads 7758 I have taken here. Now this combination says I have to multiply dead load by 0.85. So 0.85 dead load, I take here this. 1.5 wind load, it is this one. 1.5 shear load, it is this one. But for this wind load, this is actually acting on two walls. As I said before, that wind load is acting in this direction. So these two shear wall is taking that two loads. So these total load what I got in these places, like here in diagrams, everything will be divided by 2. That's why this divided by 2, it gives 26,532 kilonewton meter per wall, and 1341 kilonewton per wall. This is shear, this is moment. So now for designing, we will go for next video. Right now we are stopping up to here because my first part of the video was to calculate the wind load. So second part of the video will be up to this, to calculate total axial load, and I mean these dead loads as well as live loads. This one already I showed this wind load, but here I have shown how to calculate for one wall, and this is shear. So we are up to this level now. In the next or third video, I shall go, or I shall discuss how I can design the shear wall using all these loads. I think that's all for today. In this video, I have taken all the loads what I got, especially this for the moment due to wind loads, shear also due to the wind loads. These two I have taken this from first video. Now in this video, I mean from second part of the video, I got this. This is axial load, dead load plus live load. 7758 and 1817. So here I showed this is the moment which I got from wind load, I mean this MF. This is shear also which I got from wind loads. This is VF, and vertically this PF axial loads due to dead load and live loads. As well, we have calculated shear wall 250 millimeter width and length is 6900 millimeter. Our next video, I mean in third video, I shall use all these values to design the shear wall. I think that's all for this second part. Thanks for watching.